Okay, good afternoon, everyone. So I have two general information. So firstly, we plan to take some conference picture after Akimasa's talk in front of this building. So please go to the front of this building. But it's slightly raining, so if it is raining, maybe we will postpone the picture. Secondly, today we will have a banquet from 7 o'clock, and later I will show you the place of, actually the place is the second floor of university cafeteria, and you can go, so you can see the map on our web page, and also around this time I will be in front of this building, so if you want to go with me, just please come the front of this building on this time.
Okay, so let's start the afternoon session. The first speaker is Akimasa Miyake. He will talk about symmetry, geometry, and topology in MBQC.
Thank you very much. First of all, I'd like to thank organizers, in particular the Takanagi-san and Morimae-san for inviting me to this workshop. So following the Robert Lausendorff talk in the morning, I'd like to talk about measurement-based computation, but with slightly different focus, namely the emphasis is on the symmetry and geometry and the partially topology. So I think somehow the Robert and I join forces today to talk about measurement-based computation to essentially convey the message this model might give you new insight to understand, like the question in high energy physics. And as you know, the majority of the participants in this workshop are working on high energy physics. So I like to provide rather unconventional motivation to my work. But actually, this motivation is close to my heart. So as you know, when entanglement is present, we see a lot of interesting correspondence, and you might consider their kind of bulk and boundary correspondences. In the context of the high energy physics, in particular ADS-CFT correspondence, at the bulks, we have some, the quantity related to geometry or gravity. On the other hand, at the boundary, we like to somehow match this quantity with correlations or complexity or something like that. For example, the celebrated Ryu-Takayanagi formula really somehow manifests this equality, nicely, so that we like to have a lot of such concrete mapping between two objects. In quantum information, we like to somehow have the similar things to some extent, although I don't work on, in particular, gravity in my talk. However, still this bulk boundary correspondence is present, in my opinion. And in my talk, you will see that I see particular lattice geometry in two-dimensional setting or symmetry at the bulk. And I like to match this property as a boundary to consider these quantities, similar correlations or possibly complexity. Or today's talk is actually specialized to understand the universality in the context of the computation. And as you may notice by Lausendorff's talk, computational universality is very the robust notion, so to say. So in the quantum information, we work with the motto, information is physical. So we somehow now think if we like to understand physics, we have to a little bit think about information. And if you start thinking about information, it's natural to think about complexity because the complexity is built on information. And so naturally, people already consider in the context of the computer science to characterize complexity, and usually we have to introduce the computers, or technically they call Turing machine, to characterize or count really how many space do you need or how many time do you need, for example. And the universality is the idea to represent essentially your model is universal in the sense that if you have the one model, you can represent another any universal model. And this notion is very robust in the sense that although there are many possible definitions for computation, the traditional definition is Turing machine, or in the quantum computation, you may imagine the quantum computation is quantum circuit model or the other adiabatic models, but we call all these models equivalent in the sense that all models are universal. And if you also consider there's general way to somehow map one model to another model, and this essentially guarantees that your model is complex enough to capture anything happening in our universe. And already, we have a universal classical computer here, so certainly we like to somehow capture this notion in the context of the quantum computation. So in my talk later, I phrase this notion more specifically, but the goal is as you may guess from the Robert's talk, we have entanglement in bulk, and we like to have certain nice property. For example, determined by symmetry. And the goal is I like to somehow have the capability to produce any state at the boundary. Okay, so in the language of the quantum circuit, I'm simply saying that I like to have the capability to produce arbitrary state, by using certain gates, and I like to have the enough toolbox to guarantee this capacity. And to motivate more why somehow the MBQC is interesting, in my opinion, this is a way to connect entanglement to computation, or more specifically, computational complexity. So after providing very brief introduction on how MBQC works, I like to make kind of the tempting analogy with so-called the Page-Utah's timeless construction of time. This might be some interesting connection, and later I like to explain why in the framework of the measurement-based computation, we really somehow make this equality precise. So if we like to capture in particular computation or computational complexity, you can always count in terms of entanglement and classical communication. So I attended workshop, for example, the last week, and I hear a lot of words, the entanglement, LOCC. And I know that this, and everybody knows that entanglement is not increasing under LOCC. But often we are not really familiar with classical communication in physics, because if you look at field theory, well, we don't consider classical communication so explicitly. But the idea is in order to make this equality precisely, we have to a little bit pay attention to it. This also somehow point to the fact in the discussion of the high energy physics, often you characterize the entanglement entropy or mutual information or these entropic quantities, but they capture different physics. Okay? And the point I like to little bit emphasize is generally speaking, entanglement and correlations are different objects. And you have to use right operation measures depending on the context you like to analyze. And in particular, classical information is important if you like to capture complexity, so to say. So in order to explain this the latter part, I really like to explain very baby introduction of the measurement-based computation. So probably we already learned many times about the cluster state or the graph state in general, but let me just give a quick summary again. So essentially we are only considering so-called stabilizer state, but the graph state formally is convenient in the sense that we have one-to-one correspondence between a state and graph. So formally, if you like to define graph state, you consider arbitrary graph, and your qubit is sitting at the vertices, and your edge correspond to the particular interaction. And in this notation, we usually consider so-called control phase gate, which is 2-qubit gate with -1 sign only when two states are 1 here. And my first state is the +1 eigenstate of the power x operator. So the given graph, you essentially follow this rule. Namely, you prepare all state in the plus state and apply control phase gate according to the pattern of graph. And I also somehow emphasize this graph is not quantum circuit per se. So if you like to consider graph state generated by quantum circuit, all graph states are made by constant one depth circuit. Namely, somehow, since if you prepare plus state, and all control phase gates are commuting with each other because it's diagonal in one basis, the order doesn't matter in applying control phase gate. So in principle, the depth is 1 in quantum circuit. So this is not quantum circuit, but rather a way to somehow capture the pattern of the interaction. And the important fact is, as I already hinted, all graph states are stabilizer state in standard jargon, in the sense that the stabilizers are made by the Pauli X and the Pauli Z operator on the neighbors. Namely, for every vertex, you consider X, and you have to put the Z operator on the neighboring sites. And if you look a little bit, you will notice that all these operators commute each other because the essential overlap between X and Z happens twice, or even times in general. So that's the graph state, and this is good canonical representation of the stabilizer state in the sense that any stabilizer state can be mapped to the graph state up to local unitaries. And just as a technical note, you might think this can be done by Clifford, but actually you need generally the local unitaries. And as you can see, Oldham has a famous example of the multi-parted entangled state can be characterized this way. And just, again, this is too trivial maybe to most of people, but just to be concrete, essentially the graph states are good toy state to capture the way of the multi-parted entanglement. And for the 2-cubic case, you can easily compute this is essentially the Bell state. And for, of course, you can just write down explicit in computation basis. But if you notice that the control phase gate is essentially you apply identity if 1 is 0, and you apply control phase, sorry, the sigma z operator if the control is 1, for example, for 3-cubic case, you can only expand in the middle and apply this operation. So if the middle is 0, you apply identity. On the other hand, if the middle is 1, you apply control z operator on plus state, which flips the sign. So essentially, it becomes GHZ-like state up to basis. Okay, so as I claimed, if you change the basis, you can map to the standard GHZ state. Interestingly, if you follow this pattern, for example, the chain of this the control phase gate doesn't give you GHZ state in general. Okay, so it's straightforward calculation to see that this is not GHZ state, but we usually call cluster state. And one thing I like to explain a little bit is the mechanism of the measurement-based computation. This is very simple, but there is some interesting consequence later. So just for concreteness, let's consider 2-qubit state, which is prepared by this manner. Namely, we consider arbitrary state phi on qubit 1. If you like, you can consider particular state like the plus state, and the second qubit is said to be plus state. And I apply control phase gate. So this is essentially just the 2-qubit cluster state if the phi is a plus state. And the basic principle of the measurement-based computation is this map. Colloquially speaking, the idea is if you have arbitrary state phi under a certain protocol, namely we are going to measure first qubit, then what we can implement is essentially we transfer qubit or the quantum information to the second qubit with additional rotation. So R sub z is a rotation about the z-axis by angle eta. And we do the baby mass calculation soon, but the idea is we do measurement on the first qubit, then somehow we can see easily this what's so-called teleportation. This is kind of the half of the teleportation, but we can implement this transformation probabilistically because measurement is in general probabilistic. So in principle, depending on the measurement outcome, you have the two possible different states, and this is kind of the shorthand notation. So suppose you call the outcome. Essentially, we have project measurement, which gives you two possible outcomes, and depending on the outcomes, you have different Pauli operator in general. And to confirm this is true, I'm just writing explicitly what I said. So that we apply control phase gate on phi and plus, and if you write down general state phi in this way, that's what I'm saying. And we already applied control phase gate here. Okay, and the important thing is you can somehow combine this state in many ways. So the one trivial somehow combination is you somehow factor out plus or minus state for qubit 1, and this is the rest. But the important thing I like to emphasize is there's infinitely many ways to write down same state. So suppose you somehow choose different orthogonal basis in qubit 1, so the plus eta state is this state. Okay, so this is the eigenstate of this particular linear combination of the x and y operator. So you might imagine essentially this is the projector in xy plane if you know Bloch's sphere. And again, this step is very straightforward to confirm. If you somehow factor out the different orthogonal bases, you have different state. And this is somehow the property of the entanglement. Whenever you have entanglement, it's entangled in any basis, so to say. So that's the difference to classical correlation. Classical correlation is correlated only one basis, but if you have entanglement, you are entangled in many ways. So this eta parameter is interesting later, and actually this is the reason. Essentially, you somehow notice that depending on the amount of the eta you choose, you can change the amount of the rotation you implement on the initial state phi. And that's the kind of the analogy to the so-called the Page-Utas construction. So as I highlighted, already people notice that whenever you have an entangled state, you have this notion of the relative state. If you somehow fix one qubit in particular basis, essentially you have to match up the second qubit in the same ways. So this is the idea of the relative state, and for the case of the 2-qubit example, you have one interesting freedom. So you have U1 degree of freedom, eta, to choose, if you like. And somehow this hidden parameter, eta, is similar to the essentially Page-Utas construction. So the Page-Utas timeless construction is somehow the precursor of the Feynman's clock, and the idea is very simple. So if you know about the general relativity, you might think that you like to have the so-called Wheeler-DeWitt equation. Namely, the wave function of the universe should be static, because in the general relativity, space and times are should be treated at the equal footing. So you like to somehow impose this condition. And the solution, the Page and Uta somehow propose to address, because if the wave function psi is just the zero eigenvalue ground state of the Hamiltonian, of course there is no the temporal aspect. So the solution they propose is in principle we can consider bipartite or the joint system made by clock A and B, and they are not interacting, but essentially you have just two terms. And you define the canonical clock state or the clock time A, which is just standard time evolution on A. And it is straightforward to confirm if you assume the time t is just measured by this clock state, the reduced state for B follows standard Schrödinger equation. So if you if you compute this quantity is by the t, essentially this is somehow the partial state on B, and by using this relation. Sorry, we use this relation. Okay, so we use this definition of the time, but the time in the clock system is related to the relation here, And of course, the Hamiltonian acting on the psi somehow vanishes, so that we are left with HB acting on the only on this state, and this is standard Schrödinger equation. And so you notice that the previous example I made is kind of similar to this story. If you consider, the clock state has the Hamiltonian of the Pauli operator Z, and our system is governed by sigma x operator, for example. And in principle, we can somehow put this analogy further, but before I do that, just as a quick summary of universality, so the Robert Ransendorf and the Hans Brugge somehow showed nearly 20 years ago, this cluster state is universal, in the sense that actually the family of 2D cluster state with various size is universal in the sense that you can somehow produce any state without exponential overhead. And they could somehow construct the explicit construction for non-elementary gate set for quantum circuit. So one may show that if you have the piece of the cluster state, for example, you can simulate for C0 gate in the sense that we have this cluster and measure in certain ways. You can somehow implement effectively C0 using this piece of cluster. And if you have one-dimensional chain, also you can implement arbitrary SU2 rotation, for example. And it is already known that in the context of quantum computation, if you have these gates together, and if you could apply these gates at arbitrary fashion as you like, essentially you can generate any state in Hilbert space. Okay, so that's somehow the original idea of the measurement-based computation. And in principle, this is general feature. So somehow kind of the high-level somehow idea is, in my view, the cluster state model is kind of the Page-Utah's timeless construction together with classical communication. And although I don't really explain the details of this mechanism, but if you look at how somehow the gates can be implemented, one thing you may notice is the Horebu theorem in quantum information. Although you might think the quantum information or qubit is more powerful than classical bit, but you have to be careful on Horebu theorem in the sense that if you have only one qubit, you can only extract the one classical bit. Okay, so this is fundamental. So somehow you have to use the entanglement with the interference in the clever fashion, and what we realize is teleportation is very general procedure in quantum information processing. And in the case of the cluster state, or we could consider more general state, in principle, always you have to somehow do teleportation if you like to simulate time, so to say. So I skipped the details, but this one step, so I already explained this pair of the qubit. And in order to complete teleportation, you have to send classical information because, as I hinted, always when you measure, you have randomness. Okay, so in order to somehow deal with randomness, you have to send classical information. And the fact is for one qubit state, you have to send two classical bits in order to distinguish 4 different orthogonal unitaries in one qubit. So the general teleportation tells you in order to simulate the time direction, you need one E bit with one Bell state, and you have to send 2 classical bits in the same direction. So if you like to have the time evolution, in pictorially, you have to send 2 qubits at every step to the future. And one thing I like to mention is the entanglement is static by definition. So you could somehow combine this basic principle with 2 targets here. So I have here one step, but on the next level I have 2 targets. And I do exactly same procedure. But you might wonder how we can distinguish time and space in measurement-based computation. The way we can distinguish is the way to send the classical information. So as I already said, if you like to simulate the time, you have to send 2 classical bits in the same direction, namely to the future. But if you like to simulate kind of spatial interaction or spatial direction in this model, actually you have to send the two classical bits in the opposite direction. So this is again cartoon, but suppose you have the two qubit with time evolution, you have to send the classical bit in opposite way in a way to somehow synchronize clock so that you kind of get to the the 1+1D structure in measurement-based computation. So this is a little bit abstract, but the upper level message is the measurement-based computation allows us to count space complexity. So essentially, if you space complexity is somehow the steps you have to send classical information this way, and time complexity corresponds to the somehow steps you have to send classical information this way, for example. And usually these aspects are not really emphasized in standard the talk of the measurement-based computation. But one thing we might remember is the entanglement is static, or the entanglement is more Euclidean geometry, so to say. And if you really like to have Lorentzian geometry, if you like to have real time, the measurement-based computation is the kind of the only way to somehow map the Euclidean geometry to the Lorentzian geometry, so to say, in this context. And of course, this is very theoretical and toy model, but in the long run, there might be some useful idea here.
Are you thinking of some measurement-based quantum computation or some quantum computation model kind of code as well? Or what is the situation you're
So this is essentially, so I didn't really explain this model, but this is same as the cluster state. Also, it's not really cluster state, but it's the starting from the entanglement, static entanglement, and essentially I'm doing LCC protocol. You can measure one qubit and forward the classical information.
What is local clock here?
So the idea is I can explain the offline if you like. So in the original approach of the Page-Utas, they didn't measure. Time is not measured, but you have to assume there is kind of the magic clock living in our universe, but it never somehow really interact with our own degree of freedom, and it's keep running. But in the context of the measurement-based computation, we rather use these steps. You can somehow determine how much you like to somehow push your clock forward by measurement directions. So we are doing exactly the same procedure as the cluster said here. But the only point I want to emphasize is the classical information is important to distinguish the space and time directions. And I know this is a little bit too speculative, but let's see. So in the remaining somehow time, I try to somehow study the property of the NDQC in the more conventional setting. So the question is in order to have the nice structure, we have to start from the good starting point, namely in order to have universality in the framework of the measurement-based computation. We need a special kind of the entangled state from the beginning. So the leading question is what kinds of the entangled states do we need in order to have the computational universal capability. And this is very incomplete list of the non-universal resource states. Already people look at the graph state with different to the lattice geometry, for example. And later the people also look at the tensor networks. And as it was mentioned, you might wonder, since these somehow graph states or the tensor network states are rather artificial states, or these somehow toy models for theorists, you might wonder whether somehow we can find the nice entanglement in nature, in particular in a ground state of two-body Hamiltonian. And if you like to have the realistic Hamiltonian, the consequence is you have to deal with a lot of details. For example, if you have the standard two-body Hamiltonian in a gapped phase, typically they have decaying the two-point correlation function. So that's contrast to these toy models where you can somehow put the very, well, for example, for ground state, the correlation length is 0. So you can easily cut down the correlation, or you can control correlation easily, but in more realistic state, you have to deal with this exponential decaying tail in correlation. But the upshot is still we can handle this exponential tails, and we can pretty do similar computation as the cluster state, although we have to sometimes give up some nice property of the cluster state. And the latest topic is, as already hinted here, AKT state is in the hindsight, this is essentially the precursor of the so-called symmetry protected topological ordered state. So the natural question is whether we can find what actually not only we like to find good state, but we like to find good family of state in a sense. So that's the theme of the first talk in the morning, and Robert Lansendorf somehow gave very nice introduction of this subject and gave me very nice credit. So I don't really explain this history today, but the idea is exactly what I mentioned in the beginning. So if you have the SPTO state, you might think there is nice boundary bulk correspondence to do the quantum computation, and the recent breakthrough is made by the Robert and his group members, and we know how to somehow characterize the SPTO phases which are used for universal computation in 2 dimensions. So that's kind of the new, and I like to talk about. But before I really move to the technical parts, is there any question you like to ask right now? Or maybe I blow your mind. Go ahead.
So is there any relation of this like Feynman clock idea and just the ADM foliation of PR? Like, because, okay, so, I mean, the thing is that the fact that you can think of the wave function of the universe as being static applies both in Lorentzian and Euclidean signatures. It has nothing to do with the signature.
That's right.
Then you can foliate your space-time by choosing a preferred time direction, but of course you have freedom of choosing your space-time hypersurface however you want, but they're related to local Lorentz symmetry, okay? But then you do that, and then you can get an emergent time evolution. Because the ADM Hamiltonian, you can think of it as what drives the evolution along the foliation coordinate, which is your effective time coordinate. So is this related to the Feynman, the Feynman clock? And what is Euclidean have to do with this?
Well, so the Feynman clock construction is completely different from the construction I'm talking today. So the Feynman's clock construction is a way to somehow encode history of any space-time dynamics, regardless of the Euclidean or the Lorentzian, in a static ground state. Okay, so as you said, the metric is arbitrary. But eventually, if you prepare state, you have to measure. Okay, in order to somehow get the outcome of the state. Okay, so essentially it's different mechanism. And if you like to know, I can talk more later on this. Other questions? Okay, so let me just move to the technical part. So I like to somehow characterize the 2D SPTO phase of the cluster state in 2 dimensions. But the idea is, as Robert suggested, we like to figure out what is the right symmetry to protect the phase. And this is joint work with Austin Daniel, who is the PhD student at UNM, and the Raphael Alexander, who is a postdoc at our center. So you somehow listen to the concept of the symmetry protected topological orders. In my talk, I shortly say the SPTO, and already somehow Fernando Blanda made the great introduction on this subject, so that I can be a little bit quick today as well. So the conventional definition is that you like to consider somehow global symmetry, which for which your state is invariant. So typically, well, we consider discrete abelian group Z, and this is copy of for example, Z2 symmetry. So the Z2 symmetry is kind of the Ising symmetry. So you have you have symmetry when you exchange 0 and 1, for example, for qubit. And for cluster state, if you remember stabilizers I define, the goal is if you have only X-type symmetry, essentially somehow they are the symmetry in this sense. So I have the next slide soon. But for cluster state, you may somehow recognize if you apply symmetry operator, which is X everywhere, actually cluster state is invariant. Okay. And in this talk, we mainly somehow restrict our attention to X measurement. So although I didn't really explain, in principle, you may use the other measurement. But if you like to have somehow the scheme which doesn't depend on the detail of the state, you have to somehow resort to the kind of nice property. And somehow the family of state we are going to define share the same symmetry. Okay, and they are related to the X measurement. So if X measurement works on the one state or the cluster state, by construction, somehow the X measurement works for all states in the same phase. So I elaborate this part, but in today's talk, you notice that I mainly focus on X measurement. Phrase differently, if you can use, for example, G measurement, for cluster state, you can easily change your somehow underlying lattice structure. Okay, so I kind of hinted in the previous slide, this one. Okay, so the Z measurement is a kind of deleting qubit effectively. Okay, so that you can somehow carve out the quantum circuit picture as you want, but this is not what we are doing in this talk. Okay, so that given lattice structure, we have to live with the given lattice symmetry. And this gives us the different, possibly the capacity regarding computational universality. So just for quick review for periodic boundary condition of the one-dimensional cluster state, you might consider Hamiltonian is made by some of the stabilizer, and this is stabilizer. Okay, as I say, X, and you need Z on the neighbors. And all-term commute, and you can confirm that you have a unique ground state, and that's the cluster state in one-dimensional lattice. And you can also confirm that if you apply the Pauli X operator everywhere, the cluster state is invariant. And more interestingly, actually, you may find a pair of the Z2 operator. So the one X, suppose you only apply X operator on even side, this commute is Hamiltonian, and the state is invariant. And similarly, if you apply the X operator only on the odd side, a cluster state is invariant. And as a matter of fact, in order to protect the one-dimensional SPTO, at least you need 2 copies of Z2 symmetry. And the interesting happens at the boundary, as I hinted. So if you modify boundary, and for example, in this case, I like to have open boundary condition, so that I little bit, in this example, I drop the first term here. So I cut this edge, and I somehow have the open boundary condition. And it's somehow similar story with the error correction code. If you somehow lose one stabilizer state, you have the twofold degeneracy because you miss the one stabilizer generator. And in this case, you might think the logical X operator is effectively somehow the stabilizer you dropped, namely the X times Z, and the logical Z operator is Z operator. And the boundary bulk correspondence I hinted is although somehow these logical informations are somehow located near the boundary, if you like to respect symmetry, you cannot use Z operator. Okay, so this operator breaks the symmetry. So in order to somehow commute with your symmetry, you have to somehow cancel Z operator. Namely, you have a lot of the other stabilizer operator, so if you cancel this Z, essentially this operator is like the product of the X operator at the odd side, and this is almost the X operator at the even side. And the message is, if you like to somehow respect symmetry, this state looks like topological order state, in the sense that although somehow in order to you have the essentially logical information encoded, and in order to update or to change this information, you have to somehow apply operator everywhere on the bulk to map the one ground state to the another state, as long as you respect symmetry. Okay, so that's somehow the bulk boundary correspondence we have in measurement-based computation. And apparently this yes.
On the left-hand side, the NTP, but the right-hand side.
Yes, that's an excellent question. Then you have to notice I really somehow I didn't put the equality. So of course, as I said, I modified the boundary. So technically, I have to modify the another boundary. Okay, and technically speaking, I have the additional Z operator in the end. But the point I only like to make for now is this is bulk operator. Okay, so if you do seriously, we need the Z operator to be anti-commuting, of course. Good point, thank you. So this is more formal definition of SPTO nowadays. So as you already see, if you have SPTO, you can somehow tell whether your state is SPTO or not by looking at the boundary. And if you have non-trivial SPTO, you have this emergent edge state, so to say, in the jargon of the condensed matter physics. And essentially, you have the Pauli operator. And this is more formal statement. Usually, people prove this statement using matrix product state. But as I'm saying, if you have non-trivial 1D SPTO, the symmetry is presented by projective at the boundary. Namely, as I said, I have Pauli relation, which is projective representation of Z2 cross Z2 symmetry, because generally I have this additional I factor. And this is again the one more somehow the definition. When we somehow define the symmetry protected topological ordered phases, essentially we have family of states, so that essentially we define equivalence class. So the conventional definition is made by the essentially you can find the adiabatic continuation without closing gap. More modern kind of thing, quantum information theoretic definition is made by this paper, and you can consider this adiabatic continuation is kind of the constant Davis quantum circuit, where somehow this quantum circuit respects symmetry. So as you notice, this definition is exactly parallel to the definition of the topological orders with additional symmetry constraints. So in 1D case, there is no, for example, intrinsic topological orders, but if you consider symmetry, you may define kind of the analogy or the symmetry protected topological orders like this. And cluster state is one example of such state. So if we look at the two-dimensional cluster state, there are many fancy symmetries. But let's look at the easy ones. So the first one is just quick reminder, when we call the 2D cluster state, the stabilizers are given by this form. So we have X and Z on the neighbor of the vertices P here. And you can convince yourself there is global Z2 symmetry. The way to see it is just apply stabilizer. So this is one stabilizer. Just to make sure, now we are using this fancy notation. So this is tensor network representation of cluster state. And whenever you see this wiggling line here, this is physical degree of freedom. To make it clear, this is physical degree of freedom, and the other straight lines correspond to the virtual indices, okay, in this tensor network representation. And I briefly explain the rule of this tensor network, but for now, for cluster states, the stabilizer is you apply this the Pauli operator this way. And the goal is you like to find the symmetry made by X operator, so you have to cancel this G operator. You can cancel here, or if you apply here, more. And remember that we consider periodic boundary condition in two ways, so I got rid of the odd, and also you notice that if you apply X everywhere, it's symmetry when you have the periodic boundary condition. But there are more symmetry. So this is somehow the lattice symmetry I like to study in my talk. So I explain all symmetry in the following slides. This is just hint of the subsystem symmetry. In today's first talk in the morning, we essentially had what technically I call cone symmetry later, but the one of the subsystem symmetries. But depending on the underlying lattice structure, you have different symmetry. And all my result, I consider all SPTO state which commute with these fancy symmetries. Okay, so as Robert emphasized, we are looking for family of the state or the phase of matter which has a common computational capacity. And essentially I'm going to define my target states or SPTO state which share one particular symmetry. Okay, and as I already defined, all these SPTO states are connected to the cluster state on a corresponding lattice by symmetry preserving local unitaries by definition. And in my talk, although somehow, as I emphasize, my result apply to the old SPTO state, but we can somehow analyze as if we have cluster state. And as Robert, for example, explained in the morning, essentially we have some machinery to somehow cover all state with same symmetry. So I don't really explain the mathematical the tool, but rather somehow try to somehow explain on figures. So these are symmetries we have to consider. This is global one. I already explained. The next is the so-called the fractional symmetry. When you have the K-curve graph, you notice that you can apply X operator only on one color, so to say. So the triangular lattice is, for example, the 3 curve. So if you apply the X only on the red side, all the operator on the neighbors can cancel. And similarly, that's you can do similar application for the green and blues. And remember that for the one-dimensional cluster state, of course, one-dimensional chain is 2 curve. So we have the 2 copies of Z2, for example. And for the case of this lattice, it's Z2 cross Z2, etc. So as I said. But it turns out that this symmetry is not strong enough to define computational capacity as common the property. So we have to look at the so-called subsystem symmetry, or I call sublattice symmetry today. So these are really fancy. You have to really stare closely. But remember again, we have torus, okay, double periodic boundary condition, and if you apply X only on part of this lattice, all these are cancelled. So this is symmetry. Okay, but you notice that obviously this depends on the underlying lattice. So another symmetry which appears is called one-form symmetry. This is more somehow the symmetry which appears in the context of the gauge theory or the topological code, for example. But if you consider this, for example, Kagome lattice in particular, if you apply X on the hexagon, the Z cancels on the neighbors. So we somehow distinguish this one-form symmetry from the other subsystem symmetry I showed previously. And the important point of this one-form symmetry is it's localized symmetry, and also it's deformable. If you somehow combine two generators, you could somehow make this loop bigger. And if you analyze how many generators you have, essentially you have generator which is proportional to the volume in this case. So that's the part of the reason this symmetry is distinct from other subsystem symmetries. So so these are symmetry I talk, and let's see. So this is essentially the mechanism we already had in the morning. So the idea is when we have the two-dimensional lattice structure and we consider the periodic boundary condition, and if we consider that we essentially map this two-dimensional the torus into the quasi one-dimensional structure, whether this big tensor has this subsystem symmetry. And as I show later, in order to have the nice property, we need essentially the subsystem symmetry made by the 2n copy of the Z2 symmetry, where n is the number of qubits in this direction, or the n is exactly the circumference of the torus in this direction. And just give you some hint what we are doing. Essentially, we are going to write down the tensor network, and this is notation of the symbols. And for example, this is one-dimensional cluster state. Namely, we have the arbitrary state, and as the plus and apply control phase gate. And this is just we rotate by 90 degrees, and you may use the lot of property of the tensors. And if you write down this way, you notice that our tensor should satisfy certain rules. So this is what the Robert Lausendorff mentioned briefly. And this is general property of the tensors when symmetry is guaranteed. Okay, so although somehow I'm kind of using cluster state for explanation, but the emphasis is if symmetry is guaranteed, you know that you have certain algebraic rule you can use to prove it. And of course, I'm a little bit fast here, but the reason somehow we consider later the X measurement is when somehow system is invariant, it's interesting to measure actually every physical indices in the eigen state of the power X operator. And the reason is the same as the measurement-based computation principle I mentioned. So the symmetry doesn't do anything on your state. But what we figure out is if we measure eigenstate of the symmetry operator, essentially you can do teleportation on this SPTO state. So if you remember the few rules of the tensors, you convince that essentially this tensor is pretty much cluster tensor, and if you measure, this is kind of the teleportation circuit you had originally. And the upshot is when you have the certain subsystem symmetry, you will get the quantum circuit. Sorry, I'm messing up the button. You will get the quantum circuit made by the control phase gate and Hadamard. So this is a part of the Clifford gate you get. And this is the general correspondence I like to explain later. Namely, when you have the SPTO state with certain subsystem symmetry, you will get the quantum Serre automata structure. So this is just the standard definition of the quantum Serre automata. And the idea is for Clifford gate, you can characterize easily transfer matrix in terms of the stabilizers, and usually we like to characterize so-called this transfer matrix T at every step, and T can be just determined in terms of stabilizers.
I'm lost. Should I be lost? What is psi 3 here?
Don't worry about this slide. It's pretty much not necessary. And the point I like to emphasize is the classification of the Clifford quantum Serre automata has been done already in this paper. And if you consider the quantum Serra automata, there are three kinds. One is called periodic, namely the period is constant regardless of the system size. So this is example of the periodic quantum Serra automata. So if you enter x, according to the standard rule of the Clifford gate, it becomes the xz, and this comes back x. Okay. And the second example is called glider. And for example, this Clifford circuit maps the x and its shift or the glide by one. Okay. And the rest is called fractal in the sense that the period widely somehow changes depending on the circumference. And for this particular example, you can somehow convince that in general this QCS structure is fractal. So the one somehow the key message we find is there is one-to-one correspondence between subsystem symmetry I defined and the QCA structure we get. So there. And the important things is if you like to somehow have the universal computation, you like to somehow the transfer n qubit of information, which means that you have to somehow keep tracking of the 2n generator of the Pauli group. And in order to do this, you notice that you need the 2n independent real space generators. And these are somehow generators I already plotted a little bit. So this is essentially the summary of the result we have. We consider Archimedean lattices, which are vertex translative. Namely, these are somehow the two-dimensional lattices where somehow all vertices look same locally. And the way we somehow label is the 4-square lattice, for example, uses the 4 squares at the neighbor of every vertex. And this 3, 4, 6, 4 is, you notice the triangle, square, hexagon, and square around it. And our characterization is we have the 3 real space symmetry we call the ribbon, cone, and fractal. And they have the one-to-one correspondence between the 3 kinds of the QCS structure known in Clifford quantum Serra automata. And although I don't have time to explain all details, we somehow look at the old details. Essentially, we follow the similar the analysis as the Robert made, and we somehow worked on the old details, and we somehow figure out essentially except 2 cases, we can somehow construct universal computation on these the 9 cases. On the other hand, if we have so-called one-form symmetry, apparently this prevents the transfer of the quantum information, and we somehow say that they couldn't somehow realize the universal computation phase, for example. So if you are interested, I have too many slides to explain, but for now maybe I just skip. And well, you'll see a lot of beautiful Clifford quantum Serra automata structure, but just let me show you the last slide, and that's the summary of our result. And the high-level message I have is the analysis of the measurement-based computation may be useful in the wider context in the long run. Thank you very much for your attention.
Any questions?
So do you have a classification of these subsystem SPT, like that? You said that these are all universal, but are these the only non-trivial phase or something like that? Did you know if there are others, or it's the only one?
Well, so it depends on what you are asking. So for the case of the two-dimensional Archimedean lattice, we somehow classified completely. So in general, what we saying is in general, somehow you need the, so the, oops, sorry. Let me just go to the quickly the summary slides. Yeah, so our analysis is limited to the so-called Archimedean lattices. Okay, so in this case, somehow the
Right, but for each lattice, are you saying that this is the cluster state is the only non-trivial phase for each lattice?
oh, I see. So by assumption, somehow well, we have to start somewhere. So the point is we somehow consider by construction, we include cluster state in the phase. But you may somehow, I suppose if I understand your question correctly, of course we consider you like to have the SPTO on these lattice without cluster state included.
Oh, I'm just wondering if the cluster state is if that phase is the only non-trivial phase. Are there other non-trivial phases that's not the cluster state, but still not trivial?
So then I don't have any answer for such cases. So you might somehow find the non-trivial SPTO phase on this lattice, which doesn't include cluster state, and we don't have any study today.
Any other question?
So very nice talk. I have question on how you implement the gate. Is it you are using similar to Robert's meat grinding, or there's other?
Yes,
of
the
looking
short answer is yes, and I completely somehow skipped today. Yeah, well, I can talk offline, but essentially the higher level message is whenever this particular symmetry are present, you are guaranteed to have the certain Clifford quantum cell automata structure. So that's a given. And the question is of course the Clifford gates are not universal, so you have to figure out how you can achieve general universality. And of course, it depends on the detail of the lattice, but we figure out all cases. So this is kind of non-trivial part we are proud of, but maybe I thought it's too technical today.
Any other question?
This is about your first part of your talk, and your claim about this complexity equal to this entanglement plus classical communication, which you explained, explicit example. Do you have any suggestion of some quantity which characterize this sum for some, in terms of some density matrix or such as some universal quantity which we can measure?
Well, that's hard question.
For space and time.
Yeah, so the next
any rough idea is something.
Yeah, so let's see. For the today talk, I talked about the computational universality. And this is really, the notion, very robust, but it's not somehow something we can somehow measure. I understand what you are asking. But in principle, somehow, as I hinted, the universality is the coarse-grained notion of the complexity, so to say. Essentially, you are wondering whether somehow you have capacity to compute everything or not. So it's a yes or no concept, so to say. But the next step is certainly you can think about the efficiency, and you like to optimize, for example, circuit depth or the number of qubits. And if you start doing essentially that's probably you can somehow use standard measure like the circuit depth or number of qubits, etc. And of course, it's nice if we can connect to some actions, but that's certainly the open question, I would say.
Okay, so I guess let's thank the speaker. So there will be conference photo shooting at 3. You wanna say?
Please move to the front of this building, so we will take picture. Now, please.